Hey everybody, Mr. Piercy here, and we're going to be wrapping up with our lessons on lines. Started off by simply identifying what a transversal line did by creating a couple of a set of special angle pairs when it goes across two other lines. Then we moved on to, well, what happens when those two lines are parallel? What happens to the measurements of the angles? And then the converse of those, if the angles are this, what does it tell you about the lines? Then we talked about how you found the slope of lines, parallel, perpendicular, neither, based on their slope. Writing the equations of lines, either in slope-intercept form or point-slope form. And now we're kind of getting up to the end here where we're talking about theorems specifically about perpendicular lines. Now the vocabulary term that you're seeing here isn't so much I don't think it's a proper vocabulary definition. You're not going to pull open a geometry textbook, go to the glossary and find the distance from a point to a line. This is more of an idea, kind of maybe a theorem saying that the distance from any point to a line is going to be a segment that is perpendicular through that point to the line. It is very commonly something we would think of as the altitude of something. So altitude, let's say we have an acute triangle here, and so let's say this is A, B, C. Well, the altitude from point B, the shortest distance from point B to line AC is going to be a perpendicular segment. That's why we would think of it as the altitude, because it's the shortest distance to go from point B to segment AC. I kind of think of it more like I'm going to HEB, and here are the doors to the store, and here's me. If I have to cross from where I parked to get to the sidewalk where the store is, the shortest distance is for me to just go straight across and not walk diagonally to the door, which a lot of people do, which I don't know. I guess I'm just impatient when I'm in the car and I see people doing that, just diagonally walking across the street, taking their time. So walk straight across the street when you're trying to cross something, okay? Because that's the shortest distance from one side to the other. Now here, the theorems that we're talking about, again, no, the theorem 3.8, 3.9, they're not proper names for theorems. You can think of these like maybe a linear pair, congruent linear pair theorem, or perpendicular lines theorem. But basically what the first one is telling you, we have two lines that intersect to form congruent angles that are also a linear pair. Well, the only time I can have congruent angles is in a linear pair is if we have something perpendicular to something else. So in this case, G would have to be perpendicular to H in order for the linear pairs 1 and 2 to be congruent to each other. So the next one is saying, well, if we happen to have two lines that are perpendicular to each other, A and B, well, then they're going to form full right angles, which is pretty much the definition of what perpendicular lines is anyway. Anytime you have lines that are perpendicular, they always are going to form right angles, and anytime two lines intersect each other, they always form four angles anyway. So in this case, they just happen to be right angles. So looking here at the example number 1, in the diagram at the right, it tells you that angle 1 is congruent to angle 2. So what can you conclude about the lines? Well, angle 1 and angle 2 are a linear pair, and the only time I can have a linear pair that is congruent to each other is if the lines that made them were perpendicular to each other. So A has to be perpendicular to B. Moving on here, this theorem 3.10, this is more of a corollary maybe to the last one that we saw, because if I have perpendicular lines, they form right angles. And if I have, since a right angle is 90 degrees, if I have two angles that form a right angle, in this case angle 1 and angle 2, then they have to be complementary to each other. And so that's exactly what we're saying here. So let's say we have angle ABC, and the rays that make it up, BA and BC, well, they're perpendicular to each other. So if we have this other ray, BD, then it must mean angle 1 and angle 2 have to be complementary to each other because they form a right angle. Now, this proof here is not going to be my favorite proof in the world, particularly because of the way that it uses the names of things. The first part here, I really is fine. It's given, okay? They tell us that angle 1 and angle 2 are congruent to each other. We know that, okay? So here, the next reason that we would say, well, what is theorem 3.8? I don't really like theorem, that word or that name, theorem 3.8. But that's basically saying when we have congruent that's basically what theorem 3.8 is saying. When we have congruent angles that form a linear pair, then we have to have lines that are perpendicular to each other. So here, angle 3 and angle 4 have to be complementary. Well, again, theorem 3.10 is not really the best way of explaining it. It really should say because we have right angles, then uh, how would I want to say this? Angle 3 and angle 4, I don't want to say that. Let me see. That would really kind of be the definition of complementary angles. But theorem 3.10 works because that's how they just defined it in the text, so we'll go with it. Okay, so at this point, this is where I would like you guys to kind of pause the video and try answering these two questions on your own and see what you come up with. And when you have your answers, go ahead and hit play, come back and compare what you had with my answers, okay? So go ahead and hit pause now. All right, so let's see how we did. If C is perpendicular to D, what do I know about the measures of angle 3 and angle 4? Well, the fact that they're perpendicular to each other, C and D and C and 4, the sum of the measures have to be, uh, let me back up a second. The fact that they're telling you that C and D are perpendicular to each other should let you know that the measurements of angle 3 and angle 4 both have to be 90 degrees. And that's really what this question should be asking you. Because what it's asking is basically just saying, what are the measurements, what is the sum of angle 3 and angle 4? Well, it doesn't matter if these particular angles are 90 degrees or not. I just know that 3 and 4 are a linear pair, so the sum of those two angles have to add up to be 180. But what it's really trying to make you understand is that because C and D are perpendicular to each other, angle 3 and angle 4 really should be 90 degrees. And of course, the sum of those 90 degrees would give you a total of 180. So here, in example 2, going back and looking at the example that we saw, complete the following proof so that QPS and angle 1 are right angles. Show that. Well, again, angle 1 and angle 2, that was given to you. And so the theorem 3.8, remember that was basically just saying we have congruent angles in a linear pair, and I'm writing too close together here, in a linear pair. And of course, the theorem 3.9 said anytime that I have perpendicular lines, they always form right angles. Well, I would really rather say that's the definition of perpendicular lines, rather than try to say theorem 3.9. That's a better way of writing it, I think. Okay, now here, this is a really important thing. This is a very good logic extension where they're saying if I happen to have lines that are parallel to each other, and say one of those lines is perpendicular to something else, well then that other something else also has to be perpendicular to the other line. And that's kind of what we're seeing in the diagram here. We see line H and line K, they are parallel to each other, indicated by the little arrows. Well, line J is perpendicular to line H, so since H and K are parallel, and J and H are perpendicular, then it also must mean that J is perpendicular to K. And the second one is really saying, well, let's say we have these two lines. We have line M, and line M is perpendicular to line P. But we also have a line N that is perpendicular to line P also. Because those two lines, M and N, are perpendicular to the same line, then it must mean that they are parallel to each other. That's the only way it'll happen, is if two lines are perpendicular to the same line at the same time, the only way it's going to happen is if they're parallel to each other. So these two things are, again, you can, when you read the statements, you can see that they're very much a conditional statement where they have the if-then format. And to me, one of these really kind of seem like they're converses of each other. So, but now let's see how we're going to use them. Now the examples that we have here are not the best examples. I'm going to be honest with you. They're not the best example here, but basically what it's asking you to understand, looking through the diagram that we have here, can we go through and identify why things are either parallel or perpendicular to each other? So line R and S, they're both going to be perpendicular to the same line X. Okay, so since they're both perpendicular to the same line X, then that tells us that line T must be parallel to line S. Actually, that's supposed to say R, not T. R. Line R and line S have to be parallel to each other. So similarly, X and Y are both perpendicular to line R. Well, if both of those are perpendicular to the same line, then it means that they have to be parallel to each other. Also, the next things that we can see here, line X and Z are both perpendicular to S, so that means that X and Z also have to be parallel to each other. And since Y and Z are both parallel to X, then that means Y and Z also have to be parallel to each other by the property of the transversal property of parallel lines. So go ahead and pause the video, try answering these next two questions here and see what you come up with. And when you're done, go ahead and hit play and compare your answers to mine. Okay, so example number 3. Is line C parallel to line D? Explain. Well, line C is parallel to line C is perpendicular to line A. Line D is also perpendicular to line A. So if both lines are perpendicular to the same line, then they have to be parallel to each other. So what about B and D? Is B perpendicular to D? Well, let's see. B is perpendicular to C, and A is perpendicular to C, so that means A and B are parallel to each other. It also means that, well, if A is perpendicular to D, then B also has to be perpendicular to D at the same time. Okay, now the last thing that we're going to look at here, this is probably something that you may or may not have seen depending on what your prior experience has been. There is something in in math, but a lot of times geometry is probably going to be the first time you see it. And I know I haven't talked to you about it yet, but it is something that you may have seen previously, and it is something called the distance formula. And we're going to be doing an investigation to the distance formula here very soon. So for the time being, a lot of times whenever possible, I will try and show you why something is the way it is. And I will do that with the distance formula, but for the time being, I will ask you at this point, at this time, to just kind of take my word for it. Trust me, I'm not going to lie to you. That this is the distance formula. This is find the length between 2 points on a graph. So here's our situation. What we're looking at is we want to find the length of a perpendicular segment. Now remember, this is going back to the very beginning of the lesson that said the shortest distance between two things was a perpendicular line between them. And that's exactly what this is asking us to do here. So first of all, I'm going to look at the slope between the lines that actually look parallel to each other. Uh, and I'm going to see, are they parallel? So we have 21 over 20, and the other one that we have is like, say, the other line that we have, we don't really have another point, so I guess we can't really, yeah, I have another point kind of here, but it's hard to really see it. So let's just look at the other slope between P and Q here and see what we get there. Well, looking at that one, we get a slope of 40 over 42 negative, which simplifies to be just a fraction that's negative 20 over 21. So the negative lines and the positive lines on the graph, they are indeed perpendicular to each other. So the distance now that we can see, uh, we can find that the distance that we have between P and Q, whatever that is, that's the perpendicular distance between the two parallel segments. So that's where the distance formula comes in. Now, quite frankly, a lot of times this is just going to be a calculator exercise. You can type it into the calculator pretty much the way it's written on the board. So we're going to take the x values, substitute them in just like we would for slope or midpoint, something like that. And I'm going to take the y values. I'm going to substitute those into the formula just like I would for slope. And I'm going to just type it in the calculator the way it's written out. And I'll wind up with 58. Now here they give me a length of, they're giving me a unit of measurement of inches. So I would say the distance between the two parallel sides is 58 inches. And here we're kind of coming up to the end of our lesson. It's basically kind of asking you to do the same thing. What is the approximate distance from line M to line N? Okay, so go ahead and pause the video and make sure that you have perpendicular things to begin with. And if you don't, find where it could be perpendicular. And once you find where something might be perpendicular to something else, do the distance formula between them and see what you come up with. So at this point, go ahead and pause the video, and when you're done, come back and check your answers against mine. All right. So looking at the lines here, I actually have 2 points for all 3 of the lines. So I definitely want to make sure what are the slopes between the lines. Well, we have line 1, which is really line M, and we have line N, which I called line 2, and then we have line 3, which is, it doesn't really have a letter associated with it. It's like the transversal line. If you want to, you can kind of say, well, this is line Z or line 3 or something like that. I called it line 3. So the slope of the two positive lines have the same values, so they are parallel to each other. And the third line is the opposite reciprocal of those, so they are perpendicular. So that means I want to find the slope, I'm sorry, not the slope, but the distance. I want to find the distance between those 2 points, excuse me, because that would be the perpendicular distance between M and N, or line 1 and 2. So now I'm going to go to the distance formula, and I'm going to just plug in the values for the x coordinates and the y coordinates the way it's written out for me. And when I hit enter on my calculator, I should get somewhere in the neighborhood of 3.2 units. Now I'm going to just say UN for units because this problem didn't say the distances in inches or feet or yards or anything like that. So we'll just say UN generically for the distance between them for the units. So that's pretty much it for this lesson, ladies and gentlemen. Any questions that you had for any of the explanations, or if there's anything you want to go into more detail on, by all means, make sure you email me those questions, share them in the comment section of the Google Classroom, and I'll be happy to work with you guys on whatever questions that you might have. But until then, ladies and gentlemen, thank you again for watching, and take care of yourselves and be good, all right? Until next time.